Hello, everyone. My name is Arnaud Fiorini, and I'm going to present an IDE to develop, trace, and debug cloud and HPC application. So I'm research at the DORSAL laboratory and from the University of Polytechnique Montréal. So to begin, what's specific about HPC and cloud applications is that they use specific hardware and a specific environment. And the issue is you can't develop with traditional tools on your desktop using this specific hardware that needs a specific servers to run. Now, there's also a complex tool chain and specific softwares and libraries that you have to use in order to make this hardware work as well. And so to use all these tools and hardwares, you need traditional tools are hard to use because they typically run in your own desktop and control at the distance without having access to the UI. So that's why you need new tools like cloud IDEs in order to develop more easily inside this specific environment. So first of all, thanks to all my collaborators that helped me this project and to build the IDE that I will show and present to you. So first, let's go what we will see today. So first, we will show the demonstrations of the tools. So ROCm and then Trace Compass, and all these tools have been integrated inside the Theia IDE. And then we'll see how tracing analysis has to be scalable in order to work with big HPC clusters. So first, let me explain to you what is ROCm. ROCm is an open source software initiative from AMD, and it's a complex number of libraries to run code on AMD hardware. So mainly, it is about running code on the GPU using different runtimes. So it can be OpenCL, OpenMP, or HIP. And these runtimes need specific libraries and to communicate with the hardware. And so ROCm is the compute stack to enable development for GPUs and also clusters. And more specifically, here we're going to be talking about HIP to program GPUs. And HIP is something very much like CUDA that enables you to program the GPU and write code on it. And so to understand a little bit about what we'll see today, we need to understand what is a kernel function. So to run code on the GPU, typically you need to program a specific kernel. And this kernel function is the actual code that will be compiled and executed on the GPU. So it's a bit different from what we typically see for CPUs. Instead, when we want to run a program on a lot of data on a CPU hardware, we would write a loop and then execute the same code over and over again on the same loop. And if we do that multi-threaded, then we should have multiple loops and that are dispatched on different threads. But here on the GPU, it's not you who dispatch all the code, the executions, and it's the hardware which schedules all the wavefronts. A wavefront is something that is executed on a single hardware unit and is typically around 64 work items. And when you run the code, which we see here, we have pointers to the arrays of the input and the pointer to the output if we need it. And we refer to the table with a specific index. And this index will be calculated using either threads or block dimensions, which are logical constructs that enables you to run a huge amount of threads in parallel. So in this example, we have thread index and also block dimension. And so we have a 2-dimension table. and when we use the X index. So these numbers can be also defined for Y and Z coordinates. So we can have up to 3, and it's a matter of be able to run different problem dimensions. Also, when we run program on the GPU, if we use something like HIP, we have to be able to go through these different steps. So we have to allocate space on the device first, then copy memory to the device that we need to compute on, and then we perform a kernel launch. So what is this is basically we say to the GPU which kernel functions to execute, and also we provide some parameters so that the GPU knows how to dispatch all the execution of functions on the hardware. And then when it's done, we need to copy back the result to the host to be able to read it and display the result. Then we need to free the space on the device. So this is typically done with HIP API or also CUDA. And with OpenMP, it's a bit different because we don't need to specifically do the first 2 steps and the 4th and 5th steps. This is typically done by the compiler, which will transfer and do the memory copies by itself. But we need to specify which parameters and which variables we need to copy to the GPU. So we need to specify that to the code. So first we'll do a demo with ROCgdb and see how we can debug code on the GPU. And ROCgdb is an implementation of the GPU from AMD to the GDB. So it's a fork from GDB, and they implemented some specific functions and specific paradigms to be able to debug GPU code. And typically with GPU code, we have thousands of threads, and we don't have exactly the same constructs as in the CPU. And so this is why it's needed. Some changes are needed to debug GPU code. And in this case, we used the already existing CDT-GDB adapter to be able to connect ROCgdb to the Theia IDE. And in the ideal scenario, the debugger will implement the debug adapter protocol, but in our case, it goes through an adapter because the debug adapter protocol hasn't been yet implemented to GDB. And also with the ROCgdb extension, we are able to read the specific parameters of ROCgdb that are exposed. And we added some functions to the debug adapter protocol in order to see more information about the GPU. And so we will do a little demo of that. So here I have a code which have some kernels that are implemented, and these kernels will be run in a loop, and we'll see by tracing later that some parameters are different and what that entails. Here we do some memory allocation here on the GPU, so with either call with to heap malloc. Then we compute some parameters in order to tell the GPU how to execute this function. And then we will launch some kernels with the parameters that we have. So if we debug here, so this will launch ROCgdb. And by putting a breakpoint, we should be able to break at the correct place. So this will break on the host side, but then I will put a breakpoint on the kernel side, and we'll be able to see the parameters of the GPU. So here we only have 2 threads. That's expected, and then when we break on the kernel, we will have much more threads. So here it takes a little bit of time to load all the threads. And if we look at that, we have a huge number of threads that are executed. And because we didn't break at the first step, then we're already at the 75,000 thread. Because if we look at the dispatch here, we should be able to see how much work items we have. So this is the dimension which shows the number of work items, so the number of integers inside the array that we are executing on. And we have around 7 million of that. So that means that there will be not that amount of threads, because the threads that are defined inside ROCgdb are wavefronts. And so each thread will execute 64 integers. And the integers execute in parallel, but it depends on the lanes. The lanes here are hard-coded parameters. It's just to show only. But in the future version, we should be able to load the lanes inside the UI. Also, we have queues, which are hardware queues and that are used, but are not directly managed by the user. And after that, we have agents, which are the GPU, typically. So here on the server that I'm executing Theia on, I have two dedicated GPUs, and we're able to see them. And they have 4,800 threads at the same time in the ideal case, because right now, if I look, I should have around 3,000 threads because of some limitation on the registers usage. And here, the variables are not yet available. They are copied back to the host, but the issue is they are not yet the correct dwarf information. So we don't see the variables yet, but it should be available in a future version. Now we're able to see on which thread we blocked. And so now we know that it's the 1914 thread. And in this case, we can block on conditions, and it will block the correct wavefront that hit the condition correctly. So that ends the demo of ROCgdb. We'll go back to the slides. Then we have the tracing pipeline. So basically, we trace two things. One is the performance counters, and the other is the API and the compute kernels. So this is done by having two libraries. One is ROC Profiler, and the other is ROC Tracer. And plugin has been implemented to override some functions in order to write a CTF trace. And this plugin will output directly a CTF trace, and the CTF trace, it's a format that is easily readable inside Trace Compass. So what is Trace Compass? So Trace Compass is a software that has been developed as part of Eclipse for a number of years now. And it's a tool that is able to read from multiple sources of traces, and that has a lot of different analysis on different traces. So it can be Linux kernel analysis, it can be call stack analysis, flame graph, flame charts. And so there are a lot of analysis available right now inside Trace Compass. And what is interesting is that you can input different type of traces and compare them. So for example, if you have a GPU trace, you can also trace without TNG the kernel side, and you can have both at the same time on the same view. And that is where Trace Compass is really interesting. Recently, there have been developments to implement the Trace Server protocol and to decouple the backend side of Trace Compass and the front end. And so that makes Trace Compass usable with Theia, with the Trace Server protocol. So the Trace Server protocol is something like the language server protocol or the debug adapter protocol, where instead of having multiple UI that are very coupled with the backend, we can have something that is very decoupled and standardized, so that we are not re-implementing each time we develop a UI, we're not implementing the backend, and also it enables the IDE to be able to work with different backends. And so after that, there is the Theia Trace extension that is now part of the cdd.cloud release. And this Theia extension is able to read from Trace Compass with a tracer protocol. And I will show you what has been done with ROCm. So if I go back to Theia, here we have the trace viewer. And we traced the program that we have right now with ROC profiler using the output plugin. And we're able to read that trace, and it will show the different views that are available for this trace. And in this case, we want to open the flame chart API analysis and the not the event stable, the counters. So now we have both that. In the data, there's a small issue where some kernel execution shows at the beginning of the program that are not really there. So that's why there is a long kernel execution there. And we'll see that it corrupts a bit the statistics. And in this case, we can see the program execution. And we can see that there is a loop. Each color is assigned for the kernel name. And so when the same color is shown twice, then it means that it's the same kernel. So we can see that there are 4 kernels here that are executed in a loop. And this is shown twice here because one instance of the kernel is shown in the stream and one in the queue. From a user standpoint, the user will manage the heap streams, but will not manage the queues. But sometimes if there are some errors or some scheduling issues, then maybe it's interesting to see where the kernel has been executed and in which queue. In this case, it's pretty simple because most of the time the kernels are executed sequentially. And we can see that because if we zoom in, we can see the heap calls. And when there is a heap launch, then there is a call to heap device synchronize. So this is a call which will wait for all the kernels that have been scheduled before for a specific GPU. And so the arrows show that dependencies. So for example, we have the heap launch kernel, which shows which kernel it launches. And then we have the heap device synchronize, and it will show for which kernel it waits. Then if we look at the counters, we have enabled 3 counters. One is wavefronts, so it's the number of wavefronts that we executed. And if you remember, we executed around 7 million work items. And so in this case, if we divide that by 64, which is the number of work items per wavefront, it's around 1 million. And this spike is a counter for this specific kernel. The counters are reset between each kernel execution, and that's why it's only 1 point in time. And so the counter is always after the kernel. So that's the wavefront. And if we look at the fetch size, we see that there is different size of spikes. Some are 1 million, some are less than that. And if we look back at the code, we can see that here, these executed. These kernels are executed on just 2 pointers, but the other one are executed on 3 pointers. And that's why there is a difference between fetch size. Then if we open back the trace, we can see latency statistics. And so this is statistics based on the events that are in the flame chart. And so we can look at the average, for example, execution time of the different kernels, and see which kernel takes the most time, and and then optimize that kernel. And so in the future version of the ROCm plugin, we should have some counters analysis that will enable us to optimize the different kernels that have been executed. So that's it for the demo. And then in terms of scalability, we have two main challenges. One is trace size, because for some programs, the number of kernels executed are a huge number. For example, we can execute millions of kernels for one program. And so in the simulation program, usually one step of simulation is a kernel, or it can be just a long kernel, and we just update the data with other small kernels. And these kind of programs will generate huge amount of data. So we need to be able to handle a large trace size. And some improvements are currently being implemented. So one is event filtering. Event filtering is basically looking at some type of event that are not very useful for trace analysis. So for example, if we look back on our example here, we can see that we have heap push call configuration and pop call configuration. And these calls are not that useful because they are just used when in the code we call a specific macro to launch the kernel, and the macro will do this call before doing the heap launch kernel. So they are not maybe that useful. And if we filter them, we can gain a little bit of space on the disk. Another way of reducing trace size is to use the partial state system. So that will not reduce directly the trace size, but for Trace Compass, Trace Compass uses an intermediate representation of the analysis, and this is the state system. And by using this, it enables Trace Compass to not reread the trace every time the user move inside the trace to look at different place and time. So the state system will record a lot of different states for the whole trace, and that's not very efficient. And so one way of improving that size on the disk is just recording some partially, so having checkpoints where we record the state at this point in time, and then we can know inside the file where is it, and reread the trace where the user wants the data. And so that enables us to reduce the space on disk. Another way is to reduce contention of the file system. So if we run different types of analysis, maybe it accesses the trace and the access in the trace is not very efficient. So this is mainly between indexing the trace and analysis. And typically they conflicts between themselves, and the contention is very high. And by separating the two steps, we can have a better performance. And also one way of improving is to, some analysis are typically done in memory. And because it's in memory with huge traces, it doesn't work correctly. And we have out of memory issues. And so we have to move these analyses that are very important to disk implementation so that it can scale to big traces. Another way of improving the scalability is by distributing the analysis on multiple nodes. So we typically Trace Compass runs on one node and it's one server, but it can also be distributed. And we can, for example, if we have 100 nodes that calculate a specific compute program, then we can generate 100 traces. And these 100 traces, we can dispatch them to a few nodes of Trace Compass server. And this dispatch method will enable the analysis time to be more scalable. Also, we can pre-process the trace. So, for example, we can trace 100 nodes, and we can pre-process the trace on each node. And so, if there is an issue on one of these nodes, then we can just have this pre-processing, so the state system will be already computed, and we can just copy the state system back to our user, and the user will be able to read directly the trace and not wait for the analysis. And finally, there is filtering, aggregating, compressing traces. So that's after recording, because event filtering was before recording. We filter out the events, so we do not record them. And this is the next step, so it's a post-processing step. And we filter out events that are not useful, or we filter out events that are already used by some analysis and not after that. And so we don't need these events, so we filter out them. Aggregating is basically if you have 100 nodes, then maybe you don't want to have all the traces. You just need an overall picture of what happened. And so you aggregate the different traces in a resulting summary of the execution. And compressing traces is different techniques of events compression. And some techniques are very useful for example, MPI traces. And that can be another way of scale with the number of traces that have been recorded. So to conclude, we have 3 main contributions. One of them is to improve Trace Compass scalability by implementing all the different features that I talked about just before. Another is by interfacing ROCm to handle CPU and GPU traces. So we are able to look at HPC applications and understand better what happened and how to improve on the performance. And finally, we integrated ROCgdb inside Theia, and it also works with VS Code as well. And we are able to debug CPU and GPU at the same time inside an IDE, and also we can do that even without being physically on the server. We can do that in the cloud directly. So that's the end of my talk. So I will move over to the questions. So first question, debugging with 5,000 threads is kind of scary. I'm glad you have adopted the debugger for that. Will there be any synergies done with cdd.cloud? As I see these have similar bases. It may save some work. I don't know. Yes, so for now, the ROCgdb extension is only available as a standalone extension. Also, there is some changes to the CDT adapter, GDB adapter. And so these changes need to be mainlined before being able to run that with cdd.cloud. But for sure, Trace Compass is already, the Trace Compass extension is already available as cdt.cloud. So that's something that may be of interest. And so I based the demo on the Theia Trace extension build. So second question, how much work would it be to integrate this demo that you showed with cd.cloud IDE? So I think I already answered that question a little bit, but basically we need to integrate and build the ROCgdb extension inside the cd.cloud. But then it's just a matter of having the correct plugin inside the Trace Compass server and having the GDB extension. And then that will work with cd.cloud. And the third question is, will this work with VS Code? So for now, Trace Compass is not working directly with VS Code, but there are some improvements towards that. And in the future, we should be able to work with Trace Compass and also ROCgdb inside VS Code. So I think that's all. If there are any other questions, feel free to contact me. And thank you very much for listening.